Good morning, everyone. I am S.VINODHINI, Assistant Professor of Physics, A.D.M. College for Women Autonomous, NAGAPATTINam. Let us discuss about some topics on bonding in solids and crystal structures in solid-state physics. First, introduction to solids. What defines a solid? Solids are characterized by structural rigidity and resistance to the force. The atoms, ions or molecules are packed closely together, held by strong forces of attraction. These interatomic forces are responsible for minimizing the total internal energy of the system, resulting in a fixed equilibrium position for each atom. The nature of these forces, the bonding determines the material's properties, such as melting point. It is directly related to the bonding strength of the atoms and then electric conductivity, that is free of electrical charge carriers. Next one is hardness and brittleness. It directly resistance to the plastic deformation. Next is the types of bondings. The strength of the bond largely dictates the thermal and mechanical characteristics of the resulting material. The strong primary bonds often require energies in the range of the electron volts, that is eV per bond. There are three types of primary bonding. There are ionic bonding, covalent bonding, and metallic bonding. First one is ionic bonding. These are the transfer of electrons between the atoms with large electronegativity differences. These non-directional bonds form the basis of hard, brittle crystals that are often electrical insulators. Second one is covalent bond. It is the sharing of electronic pairs between atoms. These bonds are highly directional and strong. It leads to the materials with high melting points such as diamond. Third one is metallic bond. This is the lattice of positive ions in a sea of delocalized electrons. This unique structure gives rise to the characteristic property of the metals, that is ductility, malleability, and excellent conductivity. Then ionic bonding. Ionic bonds formed between atoms of group 1 or group 2, that is highly electropositive, and group 4 or group 7, that is highly electronegative. This resulting electrostatic attraction is non-directional, meaning it acts as equally in all directions. Complete transfer of valence electron leads to the formation of cations and anions. This energy gained from this electron transfer and the resulting attraction must outweigh the energy required for ionization. Held together by strong electrostatic coulombic forces, this strong long-range force is responsible for the high melting points observed in ionic solids. Example, sodium chloride, that is NaCl. Na gives up an electron to Cl, forming Na plus and Cl minus ions, which then arrange into a highly stable crystal structure. A bond energy of NaCl molecule, that is sodium chloride molecule. The bond energy is the energy released when the ions form the crystal lattice from the gaseous ions. This release of energy stabilizes the solid structure. The depth of the potential well at the minimum energy represents the dissociation of energy of the molecule. The curve shows two opposing forces. First one is attraction, next one is repulsion. Attraction is a long-range force, that is electrostatic Coulomb force between opposite charges. Second one is repulsion. It is the short-range force. It arises from the Pauli's exclusion principle, which electron clouds overlap and leads to the increases in energy rapidly. Second one is covalent bond. It is formed by the sharing of valence electrons, typically between non-metallic atoms with similar electronegativity. The sharing mechanism is governed by the overlap of electron orbitals. Characteristics of the covalent bonding. First one is directional. Bonds form at specific angles due to orbital hybridization in diamond leads to a tetrahedral structure. This directly makes covalent solid brittle. Second one is saturated. Saturated is each atom forms a fixed number of bonds determined by its valency. Third one is strong and hard. Materials like diamonds are extremely hard and possess very high melting temperatures due to the rigidity of the continuous covalent network. Third one is metallic bonding. Each metal atom contributes its valence electrons to collective sea or gas that belongs to the entire crystal rather than single any atom. The metal structure consists of three lattice of positive ion force immersed in this delocalized electron cloud. This delocalization explains high electrical and thermal conductivity, that is, free electrons easily transport charge and heat, and the characteristic material luster. The non-directional nature of the bond allows metallic layers to slide past each other without breaking the material, leading to high ductility and malleability. Next one is hydrogen bond. This is the stronger bond. This is particularly strong type of secondary bond involving the polar interaction between a hydrogen atom, which becomes a partially positive, and a high electronegative acceptor atom, that is N nitrogen, oxygen or fluorine with a high electron density, that is partially negative. The small size of the hydrogen atom allows the close approach of the molecules, enhancing the dipole-dipole attraction. Biological significance. Hydrogen bonds are critically important in stabilizing the secondary structure of proteins, that is alpha helices and beta sheets, and in holding together the two complementary strands of the DNA. The next one is van der Waals bonding. Van der Waals forces are weak secondary interatomic bonds arising from temporary and induced dipoles in atoms and molecules. They are much weaker than primary bonds, typically 2 orders of magnitude less energetic. Types of van der Waals forces. London dispersion forces, that is induced dipoles. Fluctuating electron motions creates instantaneous dipoles, which then induce dipoles in neighboring atoms. This force is always present. Next one is dipole-dipole, that is chiasm forces, occurs between molecules with permagnetic dipole moments. Third one is dipole-induced dipole, that is Debye forces, occurs when a permanent dipole induces a temporary dipole in a non-polar molecule. Next, the comparison of bonding types. The 5 major types of bonding span a vast range of energy, from the strong primary bonds responsible for structural materials to the weak secondary bonds responsible for liquefaction of gases and molecular cohesion. First one is ionic bond. Ionic bonds, its energy is 5 to 10 electron volts. Its nature is electrostatic transfer. It is non-directional, hard and brittle. Example for ionic bond is NaCl and MgO. Second one is covalent bond. Its energy is 2 to 8 electron volts per bond. Its nature is share the electrons. It is directional, very hard and high molecular forces. The example for covalent bond is diamond, silicon and germanium. Third one is metallic bond. The energy of metallic bond is 1 to 5 electron volts per bond. It is delocalized electrons. It has high directional, ductile and conductive. The example of metallic bonds are copper and iron. Fourth one is hydrogen bond. It has 0.1 to 0.5 energy per electron volt. It is strongest dipole-dipole in nature. It has the characteristics of molecular stabilizer and low MP. Example, ice and DNA strands. Fifth one is van der Waals forces. It has 0.1 electron volts per bond. It is fluctuating and permanent. It has weak residuance and non-directional characteristics. Example, graphite. Next one is crystal lattice. What is crystal lattice? A crystal lattice is an infinite periodic array of points in space, which represents the center of mass of the atoms or molecules in the crystal. The key feature is long-range translational order, meaning the pattern of points repeats exactly throughout the entire volume of the solid. Each point in the lattice has identical surroundings to every other point, ensuring perfect translational symmetry. It provides the mathematical framework or skeleton for the crystal structure, defining the geometry but not the content, that is atoms. What is crystal? Crystal is consisting of lattice and basis. What is basis? A crystal is formed by associating an identical geometrically arranged group of atoms or molecules that are called bases with every lattice point. The basis can be a single atom, that is BCC ion, or complex group of atoms, that is NaCl, which has two atom bases Na plus Cl minus. Crystal structure is a space lattice plus basis. This combined framework depicts the physical and chemical properties of the solid connecting to the underlying geometry, that is lattice, with the atomic content. Unit cell. Unit cell is the smallest geometrical structure or figure which is by repetition in 3 dimensions generates the entire crystal lattice. It encapsulates the full symmetry of the crystal. The unit cell parameters are the length of the cell edges A, B, C and the interaction angles alpha, beta and gamma. Types of unit cell. There are 2 types of unit cell. First one is primitive cell, second one is non-primitive cell. Primitive cell contains only one lattice point or one effective atom or basis per cell volume. A non-primitive cell contains more than one lattice point, but often chosen because its shape clearly displays the rotational symmetry of the atoms. Davis lattice. In 3-dimensional, Auguste Davis proved that only 14 distinct space lattices exist which is satisfy the fundamental property of the translational symmetry, that every lattice point must have identical surroundings. These 4 lattices are grouped according to the 7 crystal systems they belong to. They classify the possible arrangement of the lattice points themselves. First one is cubic, second one is tetrahedral, tetragonal, third one is orthorhombic. Cubic structure is a simple structure, tetragonal is a simple structure but body-centered structure. Orthorhombic is a simple structure but face-centric structure. There are 7 crystal systems in Bravais lattice. The 14 Bravais lattices are categorized into 7 crystal systems based on the recurred symmetry of their conventional unit cells. These systems are defined by restrictions on the axial lengths A, B, C and the interaction angles alpha, beta and gamma. They are cubic structure. Cubic structure is most symmetrical and constrained structure. Second one is tetragonal. Third one is orthorhombic. Fourth one is rhombohedral. It is also called as a trigonal. Fifth one is hexagonal. Sixth one is monoclinic and seventh one is triclinic. It is least symmetrical and constrained lattice. The constraints on the angles and length dictate the allowed rotational and reflection symmetries of the crystal. Visualizing the 14 lattices. The chart illustrates all 14 Bravais lattices across the 7 crystal systems, demonstrating how the combination of cell geometry and centering defines the lattice type. Cubic systems are fundamental in material science due to their simplicity and high degree of symmetry. The monoclinic and triclinic systems account for the majority of naturally occurring crystals due to their low symmetry requirement. The next is Miller indices. What is Miller indices? Miller indices are a set of 3 integers denoted by H, K and L, used to specify orientation of a specific crystal plane or a family of equivalent planes relative to crystal axis. The indices are always reciprocal of the fractional intercepts the plane makes with the 3 crystal axes A, B and C cleared of fractions. Next, notation and significance. Planes are enclosed in parentheses H, K and L, while directions are enclosed in square brackets. Families of equivalent planes are denoted by curly braces and families of equivalent directions by angle brackets. A negative index is indicated by a bar over the number, signifying that the intercept is on the negative side of the axis. They are crucial for analyzing X-ray diffraction data and understanding surface energy, slip systems and crystal growth. Then, procedure for finding H, K and L. The process involves the 5 steps, systematically converts the plane's position into unique index triplet. The step 1 is define intercepts. Determine the points where the plane intercepts the axis in terms of the unit cell dimensions. If the plane is parallel to the axis, the intercept is infinity. If the plane passes through the origin, choose a new parallel plane for intercept demonstration. Step 2. Record intercept values. Write the intercept as fractional multiples of A, B and C. Then step 3. Take reciprocals, invert the intercept values. Step 4. Find LCD. Find the least common denominator LCD of the reciprocals to clear all fractions. Step 5. Reduce and enclose. Multiply all reciprocals by the LCD to obtain the smallest set of whole integers, that is h, k and l. Enclose the final result in parentheses. Next, the examples of planes. There are three types of planes, that is the 0, plane, 1, 0 plane, 1, 1 plane. 1, 0 plane intersects at x equal to 1 parallel to y and z intersects at 0. This is face plane of the cubic cell. Second one is 1, 0 plane intersects x equal to 1, y equal to 1 parallel to z. This plane perpendicular to the xy face diagonal. Third one is 1, plane intersects x equal to 1, y equal to 1, z equal to 1. This plane cuts through the diagonal corners of the cube. Planes with lower Miller indices, example 1, 0, 1, 1, 0, 1, 1, 1, have higher atomic packing density and lower surface energy, making them more stable and prevalent. Then packing fraction. What is packing fraction? The atomic packing factor AFT or packing fraction is a measure of the volume efficiency of a crystal structure. It is the fraction of the unit cell volume that is actually occupied by the atoms. This remaining empty volume represents interstitial voids, which are important for accommodating impurities and understanding diffusion mechanisms. Packing fraction equal to volume of atoms in unit cell divided by total volume of unit cell. We calculate this by assuming atoms are hard spheres of radius r that touch their nearest neighbors, and Z is the effective number of the atoms per unit cell. Next, body-centered cubic. The BCC structure. The BCC unit cell has atoms located at the 8 corners of the cube and one additional atom fully contained in the exact center of the cube. The atoms touch along the body diagonal, which has length of 4 or is geometrically equal to a square root of 3, where a is the lattice parameter, that is edge length. The coordination number is 8, that meaning each center atom has 8 nearest neighbors. Next, face-centered cubic. The FCC unit cell has atoms at the 8 corners and an additional atom centered on each of the 6 faces. This is common structure for ductile materials like gold and aluminium. The atoms touch along the face diagonal, which has length of 4r and is geometrically equal to a square root of 2. The coordination number Cn is 12, the highest possible for a sphere packing, indicating a highly efficient arrangement. Finally, summary and future directions. Solids form a ionic covalent metal and secondary bonds which dictate fundamental material properties. Lattices plus bases define the atomic arrangement with perfect translational symmetry. The 14 previous lattices are grouped into 7 crystal systems by their geometry. Miller indices identify planes HKL and directions HKL critical for diffraction studies. FCC has more efficiency than BCC, giving rise to different mechanical properties. Crystal structure provides the geometric framework necessary for advanced solid-state physics calculations. Thank you.